In this part, we are going to give definition of vector spaces and some examples. So this part is from section 4.1 and 2.8. Definition, vector space. So a vector space, first of all, is a set V of objects called vectors, satisfying all 10 rules given here. Most important two rules we are going to understand is, we are going to verify is the sum of UV denoted by U plus V is in V. This is called closability of under addition. Another one we wanted to emphasize is there is a zero vector in V. The next important rule to be a vector space is the scalar multiplication is closed, or you can say this is closability under scalar multiplication. So one example we can check is with all 10 rules is R2 is a vector space. So to check that, first of all, R2 is a set of objects of the form V1, V2, right? And then we can go through each of those 10 rules. We're not going to go every single one. We are going to go to 1, 4, 6 to check those, and others you can check it by yourself. So for any UV in R2, then U plus V is U1, U2 plus V1, V2. So by addition of two vectors, you can do U1 plus V1 and U2 plus V2, which is still in R2. This means closability. So closability under addition holds for R2. Number 4, zero vector exists. The meaning of zero vector is for any vector, if you take 0, add it by 0, then it is the same. It keeps the same value. So we know that for any U in R2, U plus 0 is U1, U2, and 0, 0. That gives me U1, U2, which is U. And number 6, scalar multiplication. So for any U in R2 and C in R, C is scalar, which means a number, the multiplication, if you multiply by a scalar, you need to multiply each entry of U by the scalar, and this is again R2. So this completes the verification of rule number 1, number 4, number 6. And you can also do the rest of the thing by yourself. Now, we can extend the previous example as following. The space Rn is a typical example of vector space. We call this as n-dimensional vector space. So each element of Rn has the form of v1, v2, vn listed in a column. And as we have seen in the previous lectures, there are geometric intuition for those vectors. And usually for n-dimensional vector space, the geometric meaning is not really clear. So whenever we talk about geometric properties, we first give examples in R2 and R3 spaces and try to visualize it or extend the concept to the Rn space. Another non-typical, less typical example. So the previous example is Rn is a vector space. This is a typical example. Now, another example, less typical, is that the set Pn of more polynomials of degree at most n is a vector space. Which means each vector, each element in this Pn is a function, and the function not something like sine function, cosine function. So for example, f of x is e to the x. This is not polynomial. Then this is not in Pn. But if you have something like fx equals x to the nth power plus 1, then this belongs to Pn. So Pn is a huge set which includes many, many functions. Now, every element of this in this Pn can be written as a canonical form, a0 plus a1x plus anxn. Now, we claim that Pn is vector space. Pn is a vector space. Let's again prove three things. First thing, if fg is in Pn, we want f plus g is in Pn. We want to prove this. So for example, because f is in An, so f of x Pn, f of x can be written as a0 plus a1x plus anxn, and g of x can be written as b0 b1x plus all the way bnx. And of course, f plus gx has the form of this, and the coefficient for the first order is this, and all the way down an plus bn x to the nth power. So that is again Pn. And number 4 is 0 vector. So for any f in Pn, f plus 0, 0 of course is in Pn. This is degree 0 polynomial, is f. So this proves the 0 vector, existence of 0 vector. And number 6, you want to prove for any f in Pn and c in R, fc So C times F, C times Fx is still in Pn. I will leave it as exercise. All right. Now, next definition, subspace. So a subset of vector space is called subspace if the subset itself is a vector space. So not every subset of vector space is subspace. So to check a subset of a vector space, it's enough to check three properties. Is zero in the subset? Is the subset closed under multiplication, addition, and is that subset closed under scalar multiplication? So here is the last example of the lecture. So U is 1, 2, V is 0, 1, both from R2 space. So this is vector space. We already know that. Now we are going to give you H1, a subset of R2, and we want to justify this is a subspace or not. So H1 is subset of R2, but it's not necessarily a subspace of R2. To justify it is subspace, we need to verify these three properties: zero and closability and closability. So we have U equals 1, 2, and V equals 0, 1. And H1 is going to be Cu plus V, Cu plus V, such that C is in R, C is scalar. So first thing I want to check is existence of 0 of this H1. So is 0 in this space, not space, H1 in this set. So if this exists, 0 has to be given as the form of Cu plus V for some C. Then 0 is Cu is 1C, 2C plus V, which is C and 2C plus 1. And in two-dimensional space, 0 vector is, if you write explicitly, this has to be 0, 0. Two vectors are the same, so these two vectors are the same, which means 0 equals C and 0 equals 2C plus 1. So this is not possible. So this is contradiction, which means 0 is not in H1. So we don't have to check the other properties. We can just stop here and conclude H1 is not a vector space and is not a subspace of R2. The next example is H2, which is given by Cu. And U is given by 1, 2. So then first, we want to try to prove 0 is in H2. So if 0 is in H2, then that means 0, 0 equals C to C. And that means C equals 0 to C equals 0. So that means 0 is in H2. So yes. Next, closability. So if for any, so for any H1 and H2 in H2, it has to be, I want to prove H1 plus H2 is in H2. This is what I want. So we can write H1 as C1 U and H2 is C2 U. Then H1 plus H2 is going to be C1 plus C2 U. So this is still in H2. So it passed the second test, closability under addition. Now, closability under scalar multiplication. For any C in R and H in H2, I want CH is in H2 or not. So the question is, so if you write CH, so we can first, because H is from H2, so let H be, for example, C1 U, then we find CH can be written as C times C1 U, which is C times C1 U. This is another scalar. So this is in H2. So yes. So we proved this is vector space. So conclusion, H2 is a vector space. And this is a subset of R2, so H2 is a subspace of R2. If we go back and see the last question, is H2 a subspace of R3? The answer is no, because H2 is formed of CUs. U is from R2. In other words, it's a subset of R2, but it's not subset. It's not a subset of R3. So it's not subspace of R3. If we at the end, I want to give interpretation, geometric interpretation of H1. What is H1? H1 is Cu plus V. So if you look at this, you can think of you are taking one step in V and taking C steps in U. So what you have is this. For H1, any points in H1 is taking one step in V, which is, this is V, 0, 1. And then C steps in U, 1, 2. So U is this is one step in U, but because C steps in U means this is the whole, you can walk over any point on this line. So this is H1, but this is H1. Unfortunately, so there's no end. If you go along this line, you're always on the line. But unfortunately, to be a subspace, you have to go through 0, but H1 is not a subspace because it doesn't go through 0. And for what about H2? H2 means you're starting from 0, the home, and you take C step in U. So what about H2? H2 is you start from here. If you take one step in U, then this is one step in U. But if you take C step, 2 step, or negative 1 step, then you can, your territory is a line, endless line, and this goes to 0. This is subspace. But if you have a line not going through the 0, then this is not subspace. All right, we're going to stop here.